Okay, we will begin in 2 minutes, right? So because we still see students coming.
Professor Yan?
Yeah.
I have a quick question about assignment 2.
Okay.
After saving the HTML files, I noticed that for the cells that had an interactive part, the HTML shows it as if I didn't run it. Is that normal?
I'm not really sure. If that's the case, you also submit the GBit notebook file. Okay.
Okay.
Yeah, along with the HTML file, just in case, so that the TA can check in that case.
Sounds good. Thank you.
You're welcome. Yeah, I see a chat. Okay, yeah, so I think maybe it's the same question. Okay, let's begin. Right, so we are not waiting. Right, so yeah, last time we have seen two kinds of parameter estimation methods. The first is maximum likelihood estimation, and the second is maximum a posteriori estimation, or MAP map. Okay, so the difference between these two methods is pretty simple. Okay, so the first method, if you look at it, right? So the first method in maximum likelihood estimation, this is something like P x theta. Okay, right? So you want to choose a theta so that your predictive model maximize the likelihood that you see the data. Okay, but here in map this method, okay, we actually swap their order, right? So x theta. What's the difference here? Okay, who can answer me? What's the difference? Anyone can answer the question? You can unmute yourself now. Yeah.
Yeah. In MLE, what we are finding is that given theta, what is the probability of it? Given theta, but in map, given data, what is the probability of it being parameters? That's what the main difference.
Yeah. So, but you are not hitting the key part here actually. So this is because I think maybe there's. Anyway, so let me just.
And even we are considering prior knowledge as well for MLE.
Yeah,
map.
that's exactly right. Yeah, so this is because let me try to.
Also, it will not sum up to a total of 1.
What? Let me try to open my Writepad just for a moment. Let me see. Yeah, it's here. So this part is actually it's actually proportional to two parts, right? The first part is P. So this is posterior. Okay, this is if we reverse it, we have this, right? So X. Okay, so this is the first part. Okay, and we also have the second part, right? So the second part is P theta. Okay. So basically, the difference is really if we consider only this part, we are not considering prior, okay? Because according to the Bayes formula, this thing is equal to this thing divided by px, okay? Divided by px, right? And if you look at the px, right? So this both are x, okay? Sorry for the handwriting, right? Okay. So this is what we see. So this is constant. That's why we really don't need it, okay? We say this is proportional to, okay? So this term and this term, they're different in the prior. Any questions? So the map method, the key information to remember is this is posterior, which means we will consider a prior, okay? And on the other hand, if we just use the MLE, right, maximum likelihood estimation, we're only consider this part. It's like for any theta, it's the same, right? This factor doesn't impact, right? So it's a uniform distribution. Let's say if your theta has two values from here to here, right? So it's uniform, okay? The probability is the same, right? So then this part doesn't matter, okay? You assume the uniform theta, you are doing MLE, okay? If you have some prior knowledge, let's say if you are trying to estimate someone's height, right? So then you probably have a range. It will not be 0, right? It will not be 1,000, right? Something like this. Okay, so you have the prior knowledge, you can integrate this. Okay, this will sometimes improve your prediction. Okay. Any questions? Yeah. So if we again, this is optimization problem. Okay, if we maximum theta. Yeah.
Did you say a posteriori means we are considering previous data, like a map, for example?
No, a posteriori means we consider posteriori probability, right? So this is posteriori probability. Okay. This posterior is equal to the generative probability times the prior, which means we are considering the prior. Okay. General probability what we consider always, right? So the part we considering the maximum likelihood estimation. Do you answer your questions?
Oh, considering prior estimations?
What?
So we're considering prior estimations. That's the max P.
Yeah. So
data.
max a posteriori method, we also consider the prior. Okay, prior times the general probability, right? Yeah. So basically, so here we have a conclusion, right? So this is sorry, the right pattern also easy to use. Let me see. Yes. Yeah, this is. You see, so here we have. I still need to. So this is the MLE, okay, maximum likelihood estimation, right? So if this part times the P theta, okay, this term becomes what? This term becomes P theta x, okay? This becomes none, okay? So basically, if you just consider MLE, you assume this part is the same. It's a flat part. It's a uniform distribution, right? So you don't have any preference on the person's height. You think the height is 0 or 1,000, they are equal likely, okay? Right. So this is what we are doing. If you don't have any prior knowledge, of course, this is the best you can do. Right? So you just work on this. Find the theta that most likely generate X. But if you already have some prior knowledge, right, you will have some knowledge integrated. You time another prior information. This will avoid some ridiculous values, let's say the person's height, right? And make your model more accurate, okay? And so Bayes estimator is even more, right? So the previous method are all called the point estimation, right? So you find the theta that maximize things, right? And then you use this theta in your model, okay? You use this theta in your model to do the prediction, okay? But here, if you use Bayes estimator, You actually consider all possible thetas. Just different theta have different probability given the data, right? And you take an integral, okay? So Bayesian estimation is very computationally expensive. And usually we will not do that, right? But of course, if you can do that, this is the most accurate. Any questions? Okay, if not, let's move on. Okay, so now let's assume that we have a Bayesian estimation with, we assume that our variable that we see. Remember, we are considering density estimation. Okay. Before this, maybe students are still a little bit confused about density estimation. Let me see whether I can. When we need a density estimation, why density estimation is useful, right? So let me see whether I can. Let me create another desktop. Right? So because this is very important. If you cannot see the motivation, then things are not helpful. Okay, so let me try to put a browser here. Oh, it's a browser. Actually, we don't need this desktop, but it's fine. So let me give you an example. Okay, so there's a model in machine learning called a auto encoder. Okay, so what is auto encoder? Auto encoder is some model that you have. So basically, you have. Let's see this image. Okay, so you have input X, right? So you have input X. We know that our machine learning model is something like. Let me use a pen here. Okay, our machine learning model is something like f theta x, right, equal to y. Okay. Right, so this is a general machine learning tree. Here, this model has actually considered two parts, right? So this is called the encoder part from X to H, decoder part, H back to X prime. So what it means is this, right? So what you have is, H is equal to maybe encoder function. Let's use F for encoder function. Okay, theta 1, right, S, okay? And then using the H as an input, you have a decoder function. Let's use G as a function, okay? G theta 2, H. Then you want to recover the original input, but it's gonna be difficult, right? This function has parameters, okay? You are fitting it. So then you have a loss function that try to close the gap between them, okay? Try to make, why? Let me try to change the mode. Okay? So you try to make X and X prime very similar, right? So a simple method is say, hey, I want to minimize their Frobenius norm, okay? So we have X minus X prime, Frobenius norm, okay? F should be as small as possible, okay? We have seen what is Frobenius norm last time, right? Basically, element-wise difference squared. I take the sum, that's it. And of course, we need to take a square root, but usually you will consider square it so that you avoid the square root operation, right? So this is encoder model, right? So this is pretty simple. Usually we will do some, let me see whether I can move this a little bit. Usually you will do, let me clear this, do a deep learning model, right? So you have multiple functions, like multiple dense layers all the way to H, the pink thing in the middle, okay? And then you will decode also using multiple neural networks, right? So, but this is actually just not so powerful. Okay, so if you want to, there's nothing generative. Okay, so neural network, logistic regression, they are discriminative models. Okay, but you can actually embed something generative here. Okay, for example, if you do variational, right? So variational. So what's the key difference? Right, let's take a look at an image. Right. So here's the difference. Okay, instead of letting your encoder directly predict the hidden low-dimensional representation here, like a compression of data that can finally recover your data, okay? Right, so your encoder is just predicting your y is not this vector itself, okay? You are predicting the Gaussian distribution here, okay? It's a mu and sigma. Of course, it's high-dimensional Gaussian, okay? Not low-dimensional Gaussian, because the hidden vector is high-dimensional, maybe Henry or something, okay? Then using the mu and sigma, you sample a point from this Gaussian distribution. So this, you embed a probability model, right? Generative model here, right? And the opposite, right? And this can sometimes improve the model important feature of this is more like, for example, why this is good, right? So this is used for generating realistic faces. Okay, so there's a model called Steigen. Okay, actually, Steigen has a loss function, not just saying your input and output should be the same, right? So almost similar, using Frobenius norm as a loss. Okay, there's another requirement that if your model the Gaussian distribution, you hope that it's kind of orthogonal, which means your different dimension. If you have a Henry dimension data, right? Your different dimensions are kind of independent to each other, right? Then the features, the hidden features you learn actually can control different components, right? So maybe you want to change your face from a male to female, okay? And sometimes you want to change your face. Let me mute this side so that we don't have any noise. And then let's go to YouTube. Okay, so for example, NVIDIA has this kind of called Steigen, okay, which is basically following a similar idea, right? So if you want to generate faces, oh, sorry, I think I muted, right? So let's mute it, okay. It's advertisement. Yeah, so basically you can change the face by changing just as a random, the seed, right? So for the Gaussian distribution, okay, you can change the male, age, and like hair color, all are different dimensions, okay? So this is how you can generate realistic faces that are different, right? So that's one use of the GAN model, okay? So I mean, one use of the generative models. GAN is another generative model, right? You do want a probability in there. It's not just that, for example, in deep learning, we have no probability model like the dense layer. Okay, that's not gonna be. So a lot of models are adding those kind of generative component into these models. Let me unmute. I think because it's a mute site. So basically, I think the previous site, Google is muted. Okay, so it's not a muted, it's tab. And so this is why we need a generative models. Okay, another example why we need a generative models. Let me see. I think there's a paper on Twitter, location prediction. Oh, maybe we can look at this paper. So there's a model called by Amazon. It's called let me see, Amazon time prediction. I don't remember that model name. Recurrent net, I think, yeah, deep AR. Okay, they have a deep AR algorithm. Okay, if we look at Amazon deep AR, I think probably we can look at the image and see whether there's a model there. Okay, so yeah, so this is a deep AR model. So what it does is basically something like this, right? So this is called the recurrent neural net, right? So from the previous input and the current data, you predict what should be the next data, next state, and then meanwhile you will emit the next data, okay? But directly doing that may not be accurate enough. What they do is what you are actually doing is estimate, so the output of the hidden layer, the model, let's assume it's a function, is estimating distribution's parameters here, okay? And then using this distribution, you will generate the final output, okay? And then you minimize the loss from it, okay? So you can see that this kind of generative models are actually quite useful to improve deep learning models that are proposed these days, okay? So here are some examples. Any questions? Basically, you will integrate this distribution, then you have probability, etc. Okay.
So you're adding hidden layers that have a Gaussian distribution, and then based on the seed, like based on the random points, you get completely different results that are useful.
Yeah. So here actually this is one use. For example, if you just predict this, right, and this to the actual output, you will have some randomness. This randomness will help you. For example, if you see an image and you want to do the caption generation, right, each time it will generate a different sentence. You have some diversity, but they all mean probably the same thing, right? Otherwise, each time you will see the same sentence, right? If it's wrong, it's always wrong. Maybe if you make it probabilistic, sometimes the sentence will be correct. Okay. And so instead of directly generate from the hidden state, right? So remember we have a function, let's say h function, let's say f function, right? Instead of generating, take the hidden layer h here as input, generate the z, which is the output, right? So what we do, we cut it into 2 steps. The first step is predict the theta, this theta here, right? And then using the theta, we have a generative model to generate this z, right? So then you have some randomness in the output. And the benefit is actually, one of the benefits is you don't see the same output each time, right? So the second benefit, it actually improves the performance, okay? You are modeling something more robust, underlying generated data, okay? Especially you think about time series, maybe there's some micro noise that you are not capturing, right? So these are following a Gaussian distribution, right? If you model that noise, actually your prediction will be more accurate, okay? You're considering that component in your model. Right. Otherwise, you will kind of fitting the model directly from hidden state. Okay, I mean fitting the noise directly from hidden state. Any questions? Yeah, if this is okay, so just to motivate while we are looking at this. Okay, so a little bit. So it's really not useless. Okay, but again, so because we are teaching fundamental machine learning, so we will not go into these advanced models. Okay. It's too distractful. Okay, here we have two observations. The first observation, x. Okay, so this is the x we want to generate, right? So we want to predict the density of it, px. Okay, we assume that it actually follows an underlying distribution which is Gaussian, right? This is a Gaussian, and let's simplify the problem a little bit. We assume the variance is a constant, right? The variance sigma is a constant. Okay, so it's and sigma both are constant, by the way. Okay, so oh no, variance is constant. Sigma is you have a prior belief. Okay, sigma itself is again following a Gaussian distribution, right? So let's assume this case. This can be, for example, the GPS coordinate, right? So for example, if you think about this case, right? So if you are estimate your GPS reading, say, hey, you are here, right? You know that GPS device has some certain error, let's say 5 meters error, okay, right? So this is always 5 meters error, okay, right? But you don't really know where this location should be, right? Maybe your true location, okay? You believe the true location will not be too far away from the, a small circle around you, right? So this will be the prior you believe, right? So it's the prior that you are in this circle is very likely to be more likely than here, right? Otherwise, you assume they are equally likely in terms of prior, okay? Right, P theta. Any questions? If not, let's continue, right? So yeah, so if we do the maximum likelihood estimation, right? So what we'll get is this one, okay? The sample mean. For this, we have derived this, right? We have seen 3 distributions, right? So Bernoulli, binomial, multinomial, and Gaussian. And for Gaussian, if we do maximum likelihood estimation, last time we see that we have taken derivatives, right? So finally, we show that the most likely point is the average point of all the data samples you see here, okay? Sample mean, right? But if you think about the map, right, the mean average precision, right? So in that case, actually, it will be a little different, okay? Oh, one moment. I think I mentioned something wrong. Okay, so for Bayesian approach is you take the integral. Okay, Bayesian estimator is again taking, but it's like a taking expectation, right? It's correct. Okay, so we are taking expectation, right? So if you think about it, you think about each theta has a probability, right? So this is like expectation, right? So each theta's true value times the probability of the theta, right? This is like taking expectation. I think this is correct. Okay, so here we want to show next is that the map, if we consider posterior also, right? The point will not be this one. Okay, it will shift to here because we have from prior belief of theta values. Okay. And so it will move you closer to mu for sure, right? So so this is by map, this method, okay? It will be equal to the Bayesian estimation, right? So the Bayesian estimation basically says we are taking expectation of theta, okay? So firstly, instead of directly computing this value, let's first think about it. Why map and Bayesian estimation have the same value here, okay? Why? Who can answer me? Because they are still two different methods, right? So if you come back to the previous slide, so there are three methods, right? So the first is the map, which means we want to find the most likely posterior probability for that theta, okay? Right? It's a theta that generates the largest posterior probability, okay? Maximum likelihood is just a generative probability, okay? Bayesian estimation is say, hey, we want to consider all possible theta values and take the mean, okay? Take the expectation, right? Not mean, expectation of theta, because you mean means something different, right? So the expectation, the value times probability, okay? Mean means probability are all the same. It's just a sample mean, okay? And so why this is the case, right? So why this map is the same as the Bayesian estimation? Why it's the same as I take expectation, right? So the answer is actually quite simple, okay? This is because we are considering Gaussian distribution, okay? Gaussian distribution is saying something like this, okay? So if you find a Gaussian distribution that maximizes your probability, your likelihood, right? This is what we are doing, posterior probability. Let's say this is a posterior probability function, okay? Here, this value that maximize your probability is actually what? Is actually mu, right? Is actually this expectation, okay? Right? So the highest point for the y, the L value, right? The probability value, the p value. For your x, it's actually the mean, okay? The mean for the distribution, right? So they happen to be the same, okay? The highest point, if you look at the x coordinate, it's exactly the mean, right? Mu is the mean, okay? So it happens that in this example, they are the same. So the problem that is remaining is why, if we consider this prior, right? So why we have this, right? So we are not having this sample mean, we will shift a little bit, right? So before doing that, let's take a look at this value here, okay? What is this value, right? So just think about these as two weights, right? So this variance, they are all constants given here, okay? And n is the number of points, okay? So sample, right? So how many number points? So they're all constant, right? So if you just treat them as a and b, two numbers, right? It's a weighted sum, right? So this is the m is what? M is if you don't consider posterior, right? So m is the most likely value, okay? But if you consider posterior, it says, hi, I really believe the location should be around mu, right? So you are taking a weighted average, okay? So you don't just, it's not just a b, it's 1 minus a, okay? Because if you sum them and them, it's equal to bottom, right? Any questions?
Professor, can you repeat this slide once again? I didn't understand.
Which part you don't understand? Because I presented for quite some time.
Last. What is the?
So
The
the
second
same. Did you understand
assumption of
do you
map
understand
and Bayesian estimates? Yeah, I understand what is different between map and Bayesian estimates. I don't know. I didn't understand why these both are equal.
Oh, okay. So yeah, let's go back to the map. Okay. Map is saying something like, let's assume this posterior probability is something like this. Okay, right? And we want to find a theta that maximizes this likelihood. It's okay. Then this theta is your theta map.
Okay.
It's okay, right? So this theta happens to be mu in Gaussian distribution. Okay. And the mu in Gaussian distribution is exactly the expected value of theta. It's okay.
Yes.
Yeah. Okay. So this is exactly the expected value of theta. So they happen to be the same. Theta base equal to theta map. It's okay.
Okay.
Yeah. So so the video is here. So maybe you have to watch it, and yeah. So we have to move on because we are a little bit below the schedule. Okay.
Okay.
Yeah, so now let's just think about it. Okay, so if they are the same, how to compute it, right? So y it's like alpha times m plus 1 minus alpha times mu, right? Intuitively, it's saying if without the constant prior, we think it's n, right? Now we should have some weight played to mu also. Okay, right? Let's go to the derivation. Okay. So let me see, is it here? No. Ah, yeah, this is okay. Let's come back. As there will be some notation difference, okay, but don't worry about it. It's basically the same thing, okay. It's just the different notations. Let me see. So in that case, I do need something. Okay. So here we go back and change it to be notation, right? So the sample are drawn from this distribution, right? And this is the constant. Okay. This thing again, we have a prior belief of it. It's a random variable. Okay. And we assume the best location mu0 and the sigma 0. Okay. It's a reverse from what we see in the slide, right? Slide we have 0 now up there, right? So here we don't have 0. Okay. But it's the same thing, right? Now, how do we compute? So because we want to compute the posterior, right? We consider map method, okay? So posterior is equal to what? We don't consider this a constant, right? So this thing times this thing, right? So this constant is times here, okay? So this D has n data items, right? So because they are independent in our machine learning model we see, right? So basically we times their joint probabilities equal. For this mu, how you likely generate the first data point, the second data point, you just time them together. Okay, this is the prior. Okay. Any questions? Okay, so now let's continue, right? So now we know that we want to find a mu that maximizes this value. Okay, we want to find a mu that maximizes. Alpha can be dropped, basically. Okay, and so let's see how to do that, right? So now we know that what is P? P is a Gaussian, right? So this is a Gaussian distribution, is constant and exponential, xj minus mu and sigma. Okay, this is because each of the data item here, the general probability follows mu and sigma, but this mu itself follows another distribution which is a prior. Okay, right. So the prior is here. Okay, so mu follows mu0 and sigma 0. Okay. Okay, so basically, so the reason I have this red box here is, remember you that, so this is a term, right? So this is n terms times together and then times this term. Okay, it's not saying something like this. Okay, and then times this n times. Otherwise, this will be times n times. Okay, it's not meaning that. Okay, an important conclusion about Gaussian distribution is this conclusion. Okay, in your probability theory course, you must see that, but you probably forget that. But that's fine. Okay, so because the reason is very simple. You have the Gaussian distribution probability, and if you time this and you also put into the PDF on the right hand side, and you expand them, you will see they are equal. Okay, right. Put simply, if you have two distributions timed together, and both are Gaussian, right? So they are joint probability, right? So it's like you think they're kind of independent, and one is from this, the other from this, and you consider if we consider both of them, the probability will be something that is a little bit different. Okay, so this part it doesn't matter, it's a constant. So because these are the model parameters, this is constant. Okay, and what really relative distribution this part. Okay, this part because the x is a random variable, right? Mu1 is a constant. We don't care about this distribution. Okay. And this will become another Gaussian distribution with mu and sigma as the mean and the variance. Okay. Again, you can verify this by just using the Gaussian distribution formula and putting there, you will see it. Okay. Just using this formula and times this using mu and 1 mu2, right? And the times this using this, you will see that. Okay. Now the conclusion is this. Okay, so if you have two distributions time together, the result is again a Gaussian distribution with mu and sigma. And the mu is a weighted sum of mu1 and weighted sum of mu2. Okay? And sigma is also computed as kind of a geometric mean of your, of these two sigma. Okay? So this is the conclusion we have here, and we will not prove it. It's some conclusion, just remember. Okay, time to the PDF of two Gaussian distribution, it's still a Gaussian distribution. and then you Google and you will find this formula. Right? If you prove it, you still need to remember. Okay. Right. So another important thing that you need to know is this. Okay. Let's assume we have a Bernoulli trial, or we have independent trial from the same distribution. Okay. If each trial we have a variance, let's say we have a variance equal to VAR. Okay. Right. And they follow the same distribution, which means their mean is the same. Okay. Now, if we take all of them together and take the sample mean, okay, take the mean, what will be the variance? Okay, so this is the question, right? So what will be the variance? The conclusion is that if you each time you sample from the distribution, the variance of VAR, if you have 6 samples, it's divided by 6. Okay, if it's like if you think, hey, each time I guess a value, the randomness is too high, maybe 100, right? But you do that sampling 100 times and take the average, it will be 1. Okay, it will effectively reduce the noise and make it small. Okay, the derivation is also very simple. Let's say you have a random variable x1 plus x2 plus blah blah blah, blah plus xn, right? If you take expectation of them, right? So there's a linearity of expectation. Okay, so basically what you have is n times each xi. Okay, right? So now if you think about taking the average, right? So this is like you also divide by n. Then it's you can see this summation and take average is an unbiased estimator, right, of the original distribution. Okay. Now let's think about the variance. Variance is computed as of your x1 all the way to xn divided by n. Okay. So this is your average value. Okay. And for that, if you let's say we consider this guy's variance, right? So it's a distance from this thing to your expectation, right? So we can compute it something like you can take the n out, but when you take n out of the variance, it will be something like this, okay? And then your variance of x1 plus x2 plus xn, okay? But the thing different from expectation is that for variance, you don't have linearity of variance unless these data are independent, which is the case in our machine learning model. Okay, we assume they are independent and from the same distribution. If that is the case, you can compute something like, n squared times, this is like a variance of x1 plus variance of x2 plus variance of xn. So you have variance of xi because they are from the same distribution, they have the same variance, okay, times n, okay? And you can cancel out 1n here, and then you get this, each variance divided by n, okay, is your total variance. Okay. So using this conclusion, we come back to here, right? So now, each xi, we have a variance, right? So variance, maybe each xi have a variance sigma, right? Now, if we have n of them, right? So it should be sigma divided by n. Okay, I hope this is okay with you guys. Another thing that you need to pay attention is this, right? So this is the one term. This is n terms, right? So now let's go back to here, right? So what we are saying is something like this, right? So now we have n such data items and one thing like this, right? So let me see. We probably still here is more convenient for us. Okay, let's see whether we have more derivation. Okay, so yeah, so now what we have is this mu1. Mu1, if we scroll up a little bit, because it's an unbiased estimation, mu1 is still mu. Okay, it's a little ugly. Mu1 is still mu, right? But if you look at the sigma, right? This sigma, because we have n items, the sigma is effectively reduced to sigma divided by n. Okay, because of the n items, right? So well, this term is the same. Okay, this is mu0 and sigma 0. Okay, and then when you add these terms here and here, and you do the calculation, right? So you see the divide by n thing, right? So it will be square and square. Okay, And then you probably want to flip up because you don't want to have something divided by n squared down there. You time n squared on both sides, okay? Then you will get our conclusion, right? So I will leave the computation to you guys if you are interested, but basically we finally work out these things, okay? One moment, I don't see the n square, right? So let me see. Oh, I believe this is because when we time n square, for example, if you consider sigma 1 is sigma divided by n, okay? So this sigma 1 becomes sigma divided by n squared. This is sigma divided by n squared. And then let me see. Sigma 2 is just sigma 0. Oh, I see. So because mu1 is actually, let me see. Oh, sorry. No, I'm wrong. Okay, this is what we derived, right? So you know, this thing should be already the variance, okay? But here sigma means standard deviation, right? Sigma means standard deviation. This sigma is standard deviation, right? So when we talk about variance, it's actually sigma squared, okay? Sigma square variance divided by n. It's not by n squared, okay? So if you have, for example, so this term, okay, this term is sigma 1 minus 2, right? So sigma 1 is this thing, okay? Then if you have n of them, it should be divided by n, okay? Because we are talking about variance. Previously, we were deriving using variance. Sigma is standard deviation. It's a square root of variance, okay? So that's why finally, if you come back to here, it's still just n, okay? It's not n squared. Okay, any questions? But I will leave the detailed derivation to you guys. Okay, you can easily compute this offline. Yeah, so if not, we will have to move a little bit faster. Just one moment. I cannot get back to control of my mouse. Oh, okay. So, yeah. Now that we have the density estimation, right? So we want to do classification, right? So how can we use this for classification, right? Using discriminant functions. Okay. So for classification, we know that what we actually want to do. I guess we actually have this. Okay. What we actually want to do is something posterior. Okay. Is something. Let me try to use this path. Yeah. So what we actually want is you know, not this thing, right? Sorry. Let me see. And what we actually want is not the general probability, which is here. Okay. What we actually want is something like this. We want a P Ci X. Okay. When you see the data item X, how likely it belong to C1 first class? How likely it belong to C2? How likely it belongs to C3? Then we take the maximum, so the most likely class, right? Who has the largest value of this? I belong to which class? Okay. But we know that this is proportional to this, right? So because this is equal to, yeah, equal. It's the only difference that you divide by px. Okay. But px is constant. Different. It doesn't matter which class you belong to, right? It's a constant. Okay. So data is, right? It's a shared term for different C1, C2, C3, right? So we don't need to include it. Okay. So that's, if you know that we already have an estimation of this is Gaussian, and we put it in this general probability, but we actually want is a posterior, right, for classification purpose. Okay, for the classification, we want the posterior. Okay, so we can define something like this, right? We time the prior, we get the posterior, right? So again, as we have been doing, right? So we don't really want to probability time together. We'll take the log so that they become two different terms. Okay. And now let's look at some running examples using this GI, this discriminant function, right? Because this removes this, basically, you know, for each class, if G1 is larger than G2, G3, right? So then it belongs to C1, class 1, okay? Any questions? Yeah, so it's a little bit. Yeah, so here why we have this, right? So I think it's pretty clear from the function. Okay, so I will not repeat what we derived last time. Okay, because we already derived this using log likelihood. Okay, so mathematical estimation. So basically, this term comes from this term. Okay, after you take log, square root at the bottom is a -1. Okay, and this log, this square and square root basically cancels, right? So because it's a 1 divided by sigma, so taking log is to the power of 1 will come to the before. So this. Okay, and finally this term, if we take the log, we take the log, this cancels with the exponential. Okay, these two cancels. That's why we only have this term here. Okay, and finally, so all these three terms, for this term, right? We still have this term, okay, which we put here, right? Any questions? If not, we continue. Okay. Now let's consider this example, right? So this example, basically, we're considering y as an indicator variable. Okay, so we consider one-hot encoding, right? So basically, if you belong to class 1 and we altogether have 3 classes, then y is a column vector 1, 0, 0. Okay, if you belong to class 2, it's 0, 1, 0. Okay, so this is our setting here. And if that is the case, the prior distribution that we can estimate, we have seen this, right? So remember, we have seen 3 distributions. The first is Bernoulli. The second is what is that? The second is multinomial, right? So it's exactly this one. Okay, the third is Gaussian, right? If you remember, the multinomial distribution tells us that, basically, we have this conclusion. Okay, I think we can go back. Sorry, let me come to the other panel, and so this is 25. Okay, so I think we have that earlier. Which page? So this is Gaussian. Okay. Yeah, so this is monomial, and then we show this. Right? So this x is the indicator variable. Okay. I think this x is the indicator variable. Okay. And we showed that the sample mean p is this. Okay, last time. Right. So we go back to 25. Okay. We are just using this conclusion here. Okay. If you are doing the classification and this is the one-hot encoding of the class, right? So then, if here what we are doing is this, right? So we are only considering y. We are not considering x, right? So we only consider y. Okay, because we are considering prior. The reason we are talking about this slide is because we are considering this prior p, this term. Okay, the other terms we already addressed them here. Okay. The other 3 we already addressed. Now we consider p. This is only relevant to the class. Okay, it's irrelevant to the x you see, right? So you don't see it. What's your prior belief? Okay, so then you just think about the table, right? So you think about let me see how to do this. You think about a data table, right? So you have the class, and you have x1, x2. And you have some value here, which it doesn't matter to you, right? So, but you do see class 1, class 2, class 3, class 1, class 2, class 2 again, okay? Right. And now, because we don't care about this term, we are considering prior, okay? So now it really becomes just a multinomial distribution, right? It's like you sample from the underlying data set for y values, right? The first time you see 1, the second you see 2, the third you see 3, next time you see 1 again, then 2 and 2, right? It's a multinomial distribution. And the estimator for the prior should be something like this, right? So the probability that you see class 1 should be what? Because all through 6 times you see 2 ones, right? So it should be 2 by 6, okay? And if you look at 3, it should be 1 by 6, okay? If you think about maybe probability 2, if you see 3 of them, so it's 3 by 6, okay? Right, so this is how we compute this prior, okay? This prior. And Let me see. I have to come back in automatic. Yeah, okay. So this is basically this prior term. Okay. So put simply, we have two terms, right? So first term is Gaussian. We assume this is Gaussian, by the way. Okay. It may not be Gaussian, right? So second term is multinomial. Okay. Because it only consider y. Then it's just a draw from 1 to 3. Okay. And now we have the shape of how to compute these things, right? And for pi, it's something like this, right? So then when you're given a table, you can compute these terms and you can do anything you want. Okay. Then the model is set. You can do prediction. Okay. And now, so actually, let me see how to do it. Actually, what we really want is this term, right? So this term, okay, because this term is multinomial. How about this term? Okay, this term, one important thing you need to pay attention is that is this conditional C, which means if you belong to class 1, maybe how likely you will generate those data items from class 1. And if you see class 3, how likely you generate data from class 3, right? So remember, each data can only belong to one class, okay? So here's what we mean here. Let's go back and using, let me see. Using a pen again to get some intuition, okay? Let's go back to that example where you have a class and you have some features, x1, x2, x3, because this is just one dimensional. Okay, we are still considering univariate data. Okay, so this one dimension, x1. Okay, so now, so the class may have 1, 2, 3, 1, 2. Okay, 5 classes, right? So now, maybe we add a 3 so that it's a little bit more balanced. Now you will have x values, maybe 2.2, 3.3, blah, blah, blah. Okay, so what we are saying here is this, right? So because each class are independent, right? So we don't consider there's any relation between class. So when we consider C1, when we consider class 1, we are selecting from the data set only these two terms, okay? Right, so only these two terms. And then we fit the data, okay? And we know that if we select those data items, the x1 values, this value should follow a Gaussian distribution, right? Then we will care about what should be the Gaussian distribution mean and the variance, right? So for this, we basically are computing something like this, right? So if you look at here, this y is an integer variable, right? So only 2 ones, so the others are 0, okay? So this is basically 2, right? Among these two, then we compute their summation of these two x1 values, okay? So basically, it's like we select a particular class and then we compute the mean, and we select a particular class, we compute the variance for those data rows that belong to this class, okay? Maybe next time you want to compute M2 and maybe S2, okay? In that case, you will select these two rows, right? And then using their X to do the computation, okay? This Y is more like a selection, right? If you belong to my class 2, then you are 1. Okay, if you are not belong class 2, I can ignore you. Okay, it's like +0. Any questions? Yeah, so now we are ready to use this model, right? So because when you see the data, this is your classes you see, you can compute the prior for each class. And now, if you compute the Gaussian generic probability, you also see all those data items, X and Y, okay? And then you can compute for each class, what's the mean and what's the sample variance, okay? And then you can put, for a particular class, you have the Gaussian, you have the other probability, right? So the multinomial probability, okay? Then you can easily compute, compute GI. But you need to do this for all 3 classes, right? First compute G1, then G2, G3 for a new data X you see, okay? And then decide which one is the largest. You say, hey, X belongs to which class, okay? Any questions? Okay, let's continue. We are a little bit behind schedule, okay? Now let's look at the discriminant functions, okay? You may remember we have 3 terms for the Gaussian, right? So why there's no, so basically, if you come back to here, This first term is a constant, right? It doesn't depend on which class, right? For class 1, class 2, class 3, you are all adding this term. So it doesn't change the relative order. We can remove this. Then we are remaining these 3 terms, okay? That's why we are there. Okay, I think I should use, yeah, we can directly jump to here, okay? Yeah, this term is removed. Then we can go here, which page? This page. Yeah, that's why we only have these 2 terms, okay? These 2 terms. Okay, now further, let's consider a special case, right? So the special case assume that all 3 classes are balanced, right? So it's unlike how many people are having cancer, right? If you believe people having cancer should be much lower than healthy people, right? Then you probably cannot take this assumption, equal prior, right? Healthy and cancer, maybe cancer should be just 2% or 5%, right? So instead of 50%, 50%. Cancer health. Okay. Now let's assume these 2 classes are the same prior. Okay. Then this term does not change their order. Okay. So we can eliminate this, right? And if we further assume the same variance, which means SI, the standard deviation is the same. Okay. Then this is also eliminated, and we are just comparing with this, right? Because this constant is also the same for all the classes because we assume for all SIs they are the same. Okay. And finally, what remains for us to use is only this term, okay? This term. And we'll drop the constant, okay? And then the sign is important, right? Because we are picking the maximum, okay? If we drop the sign, we are picking the minimum, okay? And if you look at here, so this is basically this simplified version, right? So what does this tell us? If we have equal prior and variance, then how, if we see a X, how should we assign the data? So this is very simple, right? So if you have, because we are considering univariate data, okay? You consider univariate data. So if you have M1 here, M2 here, right? Maybe M3 here, right? So what you do is if you randomly drop an X here, okay? You just see, hey, this is the smallest, right? So this is X minus N2 is the smallest, okay? This distance is the smallest, right? And then we will choose this one because it's a negation. It's a negation of a small value, right? So maybe negation 5, okay? If you think about to M1 and M3, maybe one is 25, one is 50, okay? But after negated them, right? So we have the negated sign. Okay, this is negative 25, negative 50. And we want to pick the maximum amount of them, right? So which is negative 5, right? So we will always pick the M, the distribution whose mean is the closest, okay? So this is the case we have. Hey, sorry. So yeah, this is the classification rule. Okay, you just see who is the most closer to you. So this is the near main classifier. Okay, nearest main classifier. And if you look at the shape, so I'm not sure whether you can see clearly this thing, and this thing. So basically, let me tell you this. So this is called a P conditional CI highlight Regularization. This is the Gaussian part, right? So it's a general probability, okay? So because let's say we have a mean in -2 and then the mean in 2, okay? Then we have these 2 Gaussian distributions for C1 and C2, okay? Right. Now this term is the posterior, okay? So this is X and CI, okay? As you can see, right? Posterior is what we just derived of the discriminant function, okay? Right. For class 1, it's something like this, okay? For class 2, it's something like this. What does this mean? What does this mean? Because you will pick the minimum, you will pick the maximum value amount, right? So this basically is saying something like this, right? If you are smaller than 0, okay, then let me see whether I should. Yeah, let me call it pen. Okay, if you are on this side of the curve, okay, on this side, okay, then this guy wins. Right, so the C1 wins because the C2 is below you. Okay. Well, if you are larger than 0, right, so this guy wins. So C2 comes to win. C1 is smaller than 0.5. Okay. So intuitively, this exactly is the closeness, right? So for example, if you consider these two mean values are here, if you have an x here, of course this you belong to C1. Okay, if x is here, you are still closer to C1 or C2. But if you go beyond 0, right? So then by that time you are closer to C2 than T1, right? So that's why you kind of have this kind of curve shift. Any questions? If not, we continue. Okay. Now let's make it less restrictive, right? So we still the same prior. Okay, still the same prior. But what if we have less variance? Okay, different variance, not less, because we have two, right? One less, one more. Okay, different variance, right? In that case, these two terms matters. We cannot skip them. This prior is the same. We can drop it. So we have this discriminant function. Okay. So you think about it. For different s, actually, it's like scaling to different, in different extent. Okay. Right, and their mean also different, right? So the first M1, the second is M2. Okay, so we'll have something like this, right? We'll have something like this. So let me see, we can do something like here. So what we have here is this. So this is again M1 is -2, and 2 is 2. But this time their variance is different, right? So one is more flatter, another is taller, right? So then if we look at their posterior, okay, class 2 will first wane, and then class 1 wins. Class 1 wins. Okay, finally class 2 wins again. Okay, right. Why is this happening? Okay, this is because if you are taller, which means the area in the middle is larger, then the area on both sides is going to be smaller. So you are going to be below, below this guy, right? Because the area sum to 1 for any Gaussian distribution, any distribution, right? So if you spend less area here, you spend more area on both sides. Okay, if you spend more area in the middle, then you have less area. So which means the lower one on both sides actually wins later. Okay, right? So that's why it's happening. But obviously, if your most area concentrated here, you will win in the middle. Okay, so very close to -2, you win. Okay, but far away, this guy wins, right? This is C2, this is C1. Okay. Any questions? Okay, if not, we continue. So yeah, so previously we see classification. Now let's look at how generative models can be integrated to do regression. Okay. So regression, as we said, we have this assumption, right? So we have our true values, real value is R. R is real, right? The first letter of real, okay? And R equal to fx, okay? So this is the actual function that generate R. Like let's say in the first lecture we see the sine function, okay? So f is a sine function, but we will add some noise there, right? So epsilon, okay? Like the measurement error, for example, okay? So this is our assumption of the regression function that we will have, and the line regression. Okay, so fx is unknown, but a deterministic function, right? Like sine. Okay, but you will never observe the clean data, right? So there will always some small noise. Okay, right. So this is like a quantum physics, right? So if you observe something, something changes, right? So measurement error is like you always will measure something, you will see some error. Okay, so this is our assumption. Okay, so yeah, so if pictorially we using a picture in a diagram, we can view something like this, right? So assume your regression function is a linear function, right? It's ax plus b, right? Then it's just simple line. But what your data you actually see will be these cross, right? So it's not exactly on the line. This is because you have a small Gaussian noise that shifted a little bit away from the line. Okay, so this is our model. But even if we have a Gaussian noise, let's say x sigma, right? So even if so, we still want to predict the linear function, right? So w and w0. Okay, so this is what we are trying to do for the regression model. We want to predict the function parameter theta. Okay. Any questions? If not, let's continue. Okay, so yeah, so instead of instead of predicting the ground truth f like the sign function, we don't know, right? We want to estimate it using some function that our inductive bias. Let's say the order I polynomial g. Okay, and so yeah, this is our assumption here. This is our estimated model here. Okay, and we assume that you know, there's a random noise respecting sigma square. Usually we can assume it's a constant. Right? So like your GPH device, your guessed distance will not change a lot. Okay, right? So assume it's a constant. Okay, actually it may change a lot depending on whether you have a base station to fix the GPS coordinate or not. But we assume such complication is not there. Okay, so let me see. Yeah, so now let's come back to this assumption. Remember, so our model is something like this, right? So we have an f plus epsilon. If your epsilon is a Gaussian noise with mean 0, right? There's no error by default, right? So your noise can be each time. This time you maybe have +1. Next time you have -1, right? They cancel finally. Okay, there's no bias. Okay? It's just more variance. Okay, if this is the case, you know. So you know, this epsilon is conforming to a Gaussian noise with mean and maybe a sigma. Okay, right. Now if you plus fx, the whole thing R should belong to what? Because it's unbiased, this will belong to x variance. Okay, right. So this is I think it's pretty intuitive to you guys. Okay. So now let's do this, right? So all we need to do is expand this, right? So you know, this is becomes a median, right? Okay. This is why we have this function here, right? So so the posterior is respecting this, and yes, and then this is our assumption. Okay, we are assuming that we are sampling from this distribution. This is our generative probability, right? We assume some noise here. This is how we integrate probability here, right? Otherwise, it's no probability, right? G is a polynomial, and we regress to R, right? There's no generative component. We assume there's a sigma square, then we have some probability stuff here. Okay. Now, previously, when we look at the distribution, we are considering the how to say that? We are only considering x, right? So if you look at, let's say, if we have univariate data, right? So we have the univariate data of x1, which is, you know, which maybe we have some data 2.1, 3.2. Okay, 1 point is not maybe 2.5, etc. Okay, and we assume they belong to probability p. Okay, right, and this is our observation. Now, if we consider regression, we have another thing, right? So we have two attributes together, right? Maybe if you see this, you should regress to maybe 1. You see this regress to 2. This is 1.5, etc. Right? So it's a regression function. Okay. So your observed data is not just x. Okay. You also observe r. So this is the joint probability. Okay. Of course, we can use Bayes' rule to write it like this: by condition x times probability of x. Okay. But our observation, the probability of our observed data is this one, okay, in our general probability, right? And now our x is also containing r this time, okay? And because of this, our, just one moment. Yeah, so we will take attendance, okay, that's a reminder for attendance. We will finish this slide and then we will take attendance. This and the next slide, and then we will take attendance, okay? And then we take a break. So here, basically, you see maybe 1 and 2.1, right? And you also see 2 and these. You also see these, right? So the probability that you see the whole data set is this thing, right? Because it's independent. You take the product, okay? And you know, we don't want to time the probabilities. We want to take log so that they become summation, okay? And importantly, let me see. Let's. I think I mentioned attendance someone joined. Okay, so It's okay. So yeah. Yeah, I see another person join. Okay. So, you know, this thing is this term, right? So it can be divided into two terms, right? So if we consider this L here, this is L, this is also L, this is also L, okay? But keep in mind, right? So this term is log this plus log px, okay? But pxl is constant, right? So the x is what you see, it's a constant, right? So you don't really optimize this term, right? So because no matter what the g function is, right? So the px is always that value, okay? It doesn't matter what sigma here, okay? This is like you only need to care about this term, okay? This term has their parameters, right? Has their parameters, w0 and the w, ax plus b, a and b. Right? So we can drop this term, okay? Only look at this term. Next, if we look at this term, p, okay, this is a Gaussian distribution probability, right? So let's go back to the previous page. Let me see how to do this. Yeah, let's go to this page, okay? You know, we have after taking a look, we have two terms like this, okay? Right, so, but we assume that white noise is the same, which means it's really equal variance, right? So the variance is equal. So SI is equal, okay? Right, and after taking log, we only have this term, right? So this term SI is equal for in all scenarios, this becomes constant, okay? We only have this term, and this SI is constant, right? So after taking log, GI is after we take log, okay? That's why we have that term here, okay? We have this term, right? So the SI square is taken out, right? Because this is a summation and they share this term, take out. And the exponential term is, you know, your actual value R minus your mean value, the average value, which is this term, okay, square, right? And this constant contains the other terms, like the other term with SI and also the 2 pi term, okay? We can put all of them here, but it doesn't matter, okay? If we maximize this term plus the constant, we still maximize this term, okay? Any questions? So here, remember, we assume white noise is having the same variance. So this term is a constant term, right? And this is also constant. So put simply, what we need to maximize, right? So likelihood we want to maximize is really just a negative of the summation of this term, okay? Let's observe this term a little bit, okay? This is a true value for regression, right? So if you see XL, the true value is this. And this is your guessed value, R hat, okay? Right. So what's this term? This term is the error you have, okay? How far away your guess is from the true value. And you squared. So this is squared error, okay? And you take sum. This is sum of squared error, okay? So this term is really the sum of squared error, SSE, okay? Right. If you further divide by n, then it becomes mean squared. And here, remember the negation sign here, right? It's a negative, right? It's a likelihood is negative, okay? So you want to maximize the likelihood, you want to maximize the negative of the error, okay? Which means you want to minimize the error, okay? So they are equivalent, okay? So here we want to say that if you use a maximum likelihood estimation method and want to maximize the likelihood, it's basically equivalent to minimize this error function, okay? This error function. Here you can see we remove the constant sigma 2 here, okay? Right. So here what we want to say is that basically saying that, you know, if you look at the sum of square error or mean square error, right? So mean is the same, right? Because n is constant anyway, right? Divide by n, it's the mean square, okay? The mean square error has some theoretical guarantee and relevant to maximum likelihood estimation, right? So if you think about the case with a constant noise, okay, constant random noise, right? Then they are equivalent. Okay, these two are equivalent. Maximum likelihood equivalent to minimize the sum of square. Okay. So the maximum likelihood estimate of theta is also called the least square estimate, right? So, least squares, okay? Keep in mind, there is a lot of students, when they say least squares method, the S is missed, right? This S, right? So don't miss this S, right? So let me see. This S should always be there, right? Because you have n of them, right? Each is a square, right? The n square. And so this is the least squares estimate. Okay, if you don't remember, you don't believe me, just Google and see Wikipedia whether they have this, right? Okay, let's take a break and we will continue. And after taking a break, we will take attendance, right? So let me see what's the time now. Yeah, so let's take a break and come back in 6:25. Okay, thank you. And if you have any question, you can ask now. Okay.
Hi, I had a question about saving as or downloading as HTML from Jupyter Notebooks.
Yeah.
At least for Auburn students, I know somebody posted that for like 3 and 4, it won't allow you to download it as an HTML. I emailed about it, but I wasn't sure what's the best way to download that.
Let me see. So the best way to download it is actually using the, in Jupyter Notebook file, you have the file. Just a moment. Let me see this one. Okay. Let me see whether I can add a browser to the. So we are sharing all the course videos here, okay, in the channel. And if you go to playlist, we have the machine learning videos, okay? Right, so if you come to, I think one of them we discussed.
Find this is parameter. Students are still on their way, but we are recording, so.
Let me see. Probably it should be this one. Okay, so where do we have this?
Google a bit or get familiarized. Here you have.
Yeah, so this will be my answer. Okay.
I think I just saved it. Down here you can have an ABC. Okay. And now let's say we have x equal to 1, and I want to bring 2 times x. Okay. Now if I want to save this to HTML, just file. Okay. Download as. Okay. HTML. Okay. Okay. Right. So yeah, it's just a software I use. Just Google a bit or get.
Is this okay?
Well, when I do that on my Jupyter Notebooks, it gives me an error message.
Yeah, if that happens, either you Google and try to fix it. Maybe there's some package you want to install, or
yeah, I have also same problem.
Yeah,
actually.
or you can upload the IPy notebook file directly. So the TA have to check that file because you have this error. But you need to add a message to the TA. Hey, when I export it, there's an error message. I cannot do that. I don't know how to fix this, so I'm uploading the IPy notebook file. Okay.
Yeah, you guys download Anaconda.
Say that again.
Anaconda.
You might be missing Anaconda. Did you? Yeah. Did you?
I have Anaconda, and still I got the same problem. But I talked with Jalil.
Hey,
yeah.
Hey Deepak. Hello.
Okay.
Deepak, I think even I face the same issue, but if you're using the Jupyter Lab, it won't work, but Jupyter Notebook is working fine. So I had the same issue too when I was using the Jupyter Lab, and I was not able to get the HTML files out of the IPYNB. But if if you do the same with Jupyter Notebook, you'll get it.
I use a Jupyter Notebook actually, but
and then try to update it. If you don't have the latest version of Jupyter Notebook, then
I have a
also
latest
it is not
version.
working.
I have a latest version. I talked with Jalil also, but he said to submit direct the file
IPYNB.
Yeah, IPYNB because we tried to solve it, but still it's showing some error. I don't know.
Yeah. If you cannot address it, just send the IPy notebook file. That's also fine. Okay. if you can do that, just try to save to XML, HTML. Okay, that will ease the TA's workload a lot.
Yeah,
And,
actually,
yeah.
Actually, the problem is if suppose we got some introduction or 1 and 2, it's not a problem. Only problem is there for 3 and 2, 3.9 and 3.2. Maybe I don't have a problem in Jupyter Notebook. Maybe what's wrong, I don't know.
Yeah. So if it's for those files that you cannot save to HTML, just upload the Jupyter Notebook file.
Okay.
Yeah. Okay.
Also, Professor,
Yeah.
I'm not a PhD student, but I have used the grid search to identify the best combination of parameters. Is that fine?
Yeah, that's fine. Although you will not get a bonus point, but that's fine. Okay.
Yeah, it's not about the bonus point because I felt like instead of doing all the manual work, learning grid search makes more sense. So I've just used grid search to answer 2, 3, 4 and 2, 3, 4 questions.
Yeah, you can do that. Okay, no,
Yeah.
no problem at all. Okay. Yeah.
Okay, perfect. Thank you.
You're welcome. Okay, let me see. Yeah, again, so you can each time in Canvas we will share this video, and if you like, maybe I'm too fast, you cannot follow, then you can go back and rewatch the video and stop there, think some while, and continue. Right? So yeah, because we are kind of lagging behind in the schedule, so I will move slightly faster. Okay, because we have the next written assignment, we need to release. I think we have to release in 2 weeks. So today it's unlikely we can finish this slide, but next week we will finish and release the assignment. Okay.
One thing that might speed up the lecture is if you sometimes your drawing figures kind of takes a while, and I understand like drawing with a computer mouse that's gotta suck.
Yeah, that's exactly the problem, you know.
Do you think
because I have
could provide you like a drawing utensil type thing?
They already provide me a pad, but I'm not used to use it. You know, I am still practicing. So I already have a pen. Actually, I'm using the pen.
Oh, okay, gotcha.
Yeah,
well,
yeah, it's not easy.
It's still a difficult thing.
Yeah, because I see a black pad. You know, yeah.
That's right. You don't see your handwriting as you're writing it.
Yeah. So yeah, let me see. I didn't show the video, right? So let me start the video. Yeah. So basically, we got this pad, which is totally black, and we got this pen, and it's not easy to use. So I'm still getting used to it. Maybe after 2 more lectures, maybe I will get better to it. Okay. But yeah, right now I'm still trying to play with it and get myself used to it. We are already using the device.
Okay, well, I appreciate it, Professor. I'm
Welcome.
sure this teaching method is pretty difficult.
Okay, thank you. Okay, let's begin because we are a little bit behind the schedule. Okay, so yeah, as I explained, so the pad I'm already using it, but you know it's not like iPad, so I don't see what I write on the pad. I see screen and I try to move my hand, and basically I view the screen but I write on the pad. So there are some familiarity issues, just like how we use mouse right at the beginning. Okay, so yeah, if you have any difficulty understanding my handwriting, just let me know. Okay. I think at least the pattern is not back yet. Let's wait for a few, maybe 1 or 2 more minutes. Okay. Yeah, before we take attendance, maybe some students are not back yet, but we cannot wait. Okay, we are behind schedule. Let's continue a little bit. Maybe we finish finish two more slides and then we take attendance. Okay. Okay. Yeah. So let's continue. Okay. Let's use the previous conclusion, the mean square error. Okay, to consider linear regression, which means that our g function is a linear function, right? Ax plus b, right? So here we assume it's a w1 x plus w0. Okay. Yeah. So if that is the case, basically, you know, the real value minus the estimated value, which is basically this value. Okay. And let's see. Okay. So now what we need to do, right? So because this is the sum of square error, right? We want to minimize this error. Okay. What we need to do, because it's a quadratic function, right? So this is a quadratic function, and this is convex for sure because it's quadratic. Okay. It's just like x minus a squared, something like this. Okay. Right. So but it has an a and a x1 and x2. Right? So if you consider the parameter we optimize, actually there are two values, w1 and w0. Okay. And you know, if we consider this, we take all we need to do is take a derivative to both take derivative of e to both w1 and also to w0. Right? So then we see what we will get. Okay. So for example, let me see. I think the pad is. Let me restart the pad. Okay. Now it's right. Okay. So now the first thing we want to do is take a partial derivative of e to partial derivative of w1. Okay. Right. Let's first use w0. Okay. So what will be the result? Right. So we are using chain rule. Okay. If you think about this term, let's call it u. Right. So then it's u squared. Right. So u squared, if you take the partial derivative, it becomes 2u. Right? So basically we have 2 minus w1 x minus w0. Okay. But again, this is L and we have a summation over here. Okay. And because there's a 1 by 2, okay, there's a 1 by 2. So there's also 1 by 2. So these two terms cancel. Right. And now the next, because it's a chain rule, right? Then you need to take a particular to u to w0. Okay. And if you look at u to w0, it's really the coefficient which is negative. Okay. And the first thing you want to do is set this thing to 0. Okay. So if you want to do this, set this 0 negative when it's gone, right? And let's write out this term here. Okay. This term is basically saying something like summation of L your RL. Okay. But you can move these two terms negative to the right hand side. Then it becomes, it becomes summation of L, W1 XL. Okay, W1 can be taken out. Okay, but because it's the coefficient, it's shared. Okay, and then you have also summation of W0, right? Because there are n of them, the summation is taken for n times. So this becomes plus NW0. Okay. So this is basically this term, right? NW0 plus W1 and the summation of these. Which is this term. Okay. I think it's a bit messy, so let me. Okay. So this is what we do. We first derive this one. Okay. So because some student may just come back, let's derive the second one. Okay. So let me see. Okay, I need to pull out the pen again. So then we use a pen. Okay. Now, so this is actually the first term is what? E take partial derivative W0. Okay. The second term is E take partial derivative W1. Okay. And we need to set it to 0 to find the one that minimizes error. Okay. Now let's consider this term. Okay. If we take a partial derivative of this E term to W1, what will be the result? So the first term is still the same. Okay, this is U. So U squared is 2U, and the 2 cancels with the 1 by 2. Right, so we still get this. Right, so we got L and this term. Okay, L minus W1 XL. Yeah, XL minus W0. Okay, and now the next thing we need to do is to take derivative of U, this U, chain rule, okay? Partial derivative W1, okay? Because we are considering W. And then we use a coefficient. Right? The coefficient is negative XL, right? So then we time this term with negative XL. Okay? And if you have if you look at the difference from our previous case, right? So basically this term is the same. Previously this term -1 now become negative XL. So that makes a little bit difference because this negative XL is timed to each of these three terms. Okay. Right. And then if you set to 0, you will get this. XL is associated with each term. Okay. Previously, there's no term, then the summation is just 1, right? N of them is n. Okay. Now actually it doesn't matter. Okay. So we will have each of these terms times XL. Okay, in the summation. Then we get this. I will leave the derivation details to you if you cannot immediately get this. Okay, but that's just a taking derivative. Okay, we are a little bit behind schedule. Now we can represent something like this, right? So if you look at this, is more like a linear equation. Right? We can use a w plus 1. Okay, where a is this two coefficient, right? W is w1, w2, y is this. Okay, so simply, basically, this is y, okay? This is the coefficient, okay? And we know that using linear equation, we know this is A11, A12, A21, A22, okay? So then we have this. Okay. All right, so now using this, one observation we should see is that all these n is how many data you have, right? L is a data feature, right? Because we are considering univariate, it's the only value, okay? And if you look at y is the same, right? So r is just its regressed value, right? The predict value. We want to predict the value, we want to predict the real value, okay? A and y are constant, right? W is an value we want to fit, right? So all we need to do is y is equal to A inverse y, okay? So because, it's just a time the A inverse on both sides. Look at it. This is our W estimate, right? So this will be our estimation for this function, for W1, W2. Okay, given those data. Any questions? So keep in mind, this is just a linear regression, right? So we can actually generalize it to polynomial k order, right? So first we only have these last two terms. We can go all the way to k terms, okay? And the derivation is similar. And we will first take attendance, and then we will look at this, okay? Yeah, it's here. Okay. I will sample some names, and we'll keep it fast, okay? Ran Yan. Is Ran Yan here?
Yeah, I'm here.
Okay. Yeah, student asked me whether he missed a sentence. I said no. Wang Xiaohong.
Yeah, I'm here.
Okay. Fruitvy.
Yeah, I'm here.
Okay. Connor. Connor. No. Okay. Nancy. Nancy.
Here.
Okay. Boniface. Boniface.
I'm here.
Okay. Clark. Clark. No. Okay. Saidipa. 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 No. Okay. Harish. Harish. Harish, can you repeat?
I'm here, sir.
Okay. Cole Brian.
Here.
Brian. Okay. Ahmad. Ahmad Nabil. Are you here? Nope. Lu Zhiying. Lu Zhiying. Zhiying Lu. Is Zhiying Lu here?
Yes.
Okay. Okay. And Peida Li. Peida Li.
Here.
Okay. Yeah. So please mute yourself if you know. I know I called your name. Okay. And Sri Lanka. Sri Lanka. Sri Lanka. Will you just repeat your name? Are you here? If you're here, can you repeat again? So because I need to check your name. No? Could be. Could be.
Yes, sir.
Okay. Lina Huang.
I'm
Lina
here.
Huang? Okay,
Here.
got it. Smith. Smith Jury. Smith Jury.
I'm here. I'm here.
Got it. Okay. Daniel Foot.
Here.
Okay. Vikram. Vikram, ready?
I'm here, sir.
Okay. Okay. Nikhil. Nikhil. Nikhil Damira. I do see some chat. Okay, so.
Sir, his mic is not working, sir. So he messaged in it.
Oh, okay. I see. Nikhil. Study Park. Let me see. Study Park. Did I call the name? I will come back shortly. Okay, let me call the last name. Okay. Pritesh. Pritesh.
I'm here.
Okay. Yeah, let's search. Okay. All right. Let's have the other list. For speed, we will just call two names. Okay. Mingyu Liu.
Yeah, I'm here.
Okay. E sign. E sign at Blu-ray. E sign. If I pronounce your name wrongly, just let me know. Okay. Okay, then that's it for today. Attendance. Okay, just attendance. Right, so stay with me. Okay. Yeah. All right. So next, previously we see the linear regression, right? If we can extend this to polynomial. Okay. So we can actually compute this thing, right? So let's take a look at how to compute this thing, right? So if you remember, for linear regression, it's just this corner, these four values, right? We can expand it to so many values, right? So let's see how, I see somebody just left. Maybe they should pop up some problems. Okay, so like who left, I cancel the attendance next time, maybe. Okay, yeah, let's go back and see why this is the case first, okay? So basically, our previous derivation here, it's this term. Now we have a more term. Right? So if you consider another term, let's say minus W2, right? So X L squared. Oh, let me use a pad. Let me. If you don't use a pad, it's a little bit difficult. Pad is still a little bit better. Okay. So let's say here we have another term, W2 X L squared. Right. So now, if we take a derivative, you will see that now, now the first u is still the same u, right? The second term will be now what? It will be negative xl squared, right, for w2, if we take part of it, right? So this is one more xl than before, right? So this will be something like xl squared, xl squared, xl cubed, okay? So all the others are the same. So basically, you will see if you have more polynomial terms up there, you will see this x to the power of something just increase. Okay, and that's how we get it. Okay, so you can see this increasing along this direction, also increasing along this direction, right? And then we can write in the matrix form something like this, right? So then this A matrix actually quite tricky. Okay, so the A matrix is symmetric, right? So, and you can see if you are good at linear algebra and matrix notations that A is actually kind of D square, D transpose times D, okay? And why D is this value, okay? It's kind of makes sense to some of you, right? So you can see the D is a term like this. If D transpose times D is something like this, right? So, but for most people, maybe we need to go through this, right? So let's briefly go through this because our time is very limited. Okay, so how you can see the relation immediately in the future when you see this kind of symmetric matrix. You know that you can kind of, if it's symmetric, you know it's kind of, you can take a square root, right? Because it's kind of like square, right? Yeah. So the way to see this is that you need to be familiarized with autoproduct. Okay. So we know that if you have, let's say, you have something like x1, xn, right? So one row vector times a column vector. Okay. Maybe y1, yn. What will be the result here? This is inner product. Okay, this is x1 times y1 plus x2 times y2. Okay, right. So this is inner product. Out product is something different. Right? So if you write it like this is x transpose, because x is a column vector. X transpose times y. Okay, while out product is something like x times y transpose. Okay, so it's something like this. If you have let's say x1, x2, xn. Okay, this is the version. So and then The other side becomes a row matrix. Right? So y1, yn. Okay. What will be the result? Who can tell me? I don't think I have enough space to plot. So let me try to clear up some space. Okay. Yeah, this is called outer product. Previously called inner product. Right. So if you have one row times one column is equal to one value. Okay. If you have a one column times one row, it's equal to a matrix. Okay. Right. So here's what we see. Right. So if you have a column A1 to AN. Okay. And then times a row vector, which is B1 to Bn. Okay, so the result is actually a matrix. Okay, this is A1 B1, A1 B2, A1 Bn. Okay, basically AI Bj. Okay, so the i's row and this one. Okay, this will be A and B. Okay, oh, this will be A and B1, so, and this is A and B. Okay. But how to see this? Right, so this is very simple. Right, so the first row, the first column should be the first row times the first column. Right, A will be. Okay. The second term should be what? The first row times the second column. Okay. So it's A1. Right, and then you do this for the nth row, the first column. Right. So if you follow the definition, it's very easy to see that equal, but you should not just do that. But you should keep in mind that this is outer product. Okay. It's an outer product. Okay. This is inner product. Okay, you need to get familiarized with these notations immediately, just like what we talked about the quadratic form. Okay, because any matrix, students should know this. Okay, right. So now let's take a look at this term. Okay, let's take a look at this term. And the first thing we want to do is we again, it's very difficult to see things through. Okay. The first thing we want to do, we want to eliminate the summation. Okay, let's just eliminate it. And because this is n summation 1, okay, let's also eliminate this summation here, this summation here, this summation. Okay. By doing this, I think it should be easy for you to see that it's actually a outer product of 1 xt blah 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 xt to the power k. Right. So times the same thing again, 1 xt to the power k. Okay. Right. Okay, can you see this? Right. So it's very simple, right? It's 1 and 1 is 1. Okay. The second is 1 and xt. Right. So this is basically our product because if you look at a particular term, this is what? This is xt to the power 3. Right. Why this is the case? Why it's actually xt, this is the second row, right? So starting from 1 is the first term, right? Xt is the second term, right? So this should be xt. Right. Now the third column, okay? The third column is what? Xt squared, right? This gives you this. Okay, if you can see that the ij all map with this, right? This is the first term, this is the second term, this is the third term. So this is the same vector. Okay, let's call it this is small d. Right? So this is d transpose. Oh, this is d times d transpose. Okay. I hope this is not too difficult to see. So this is our product without summation. But now, how to see this? Right? How to see this? Summation is basically saying that we have another dimension. Okay, so you know how to matrix. So now this thing. Previously, if you ignore the summation over t, right? If we don't consider t, we don't have the t. We only consider x, right? So only one t, right? So it's like this. So if we just consider one t, we have one row. Okay, all the same t. Okay. Now it's more like remember we have d times d transpose, right? So D is a column vector. So here it's like we expanded it along the t direction. Okay, so now if you times transpose of it. Okay, so this guy's transpose times this. Right? So yeah, how to say this? So let me help you visualize a little. Okay, so previously we are not taking summation, so it's the same t. Okay, so these are t. Okay, it's just a one row. Okay, and we say that it should be a column vector times a row. Okay, so the column vector is really, if you take D transpose, this row becomes the first column. Okay, this thing. Now if you have so many rows, so this becomes the second column, the third column, the fourth column. Okay, so this is D transpose, and D is something like this. Right? Now if you finally take the product, right? So you will see that they are kind of equal to summation, right? So how to see this? You can use block matrix notation, right? So let's call this, let's say this is A, B, C, D, these are the columns, okay? Then this is also, right? So this is column vector A, B, C, right? And we know that we can operate them just like a, block notation, right? So we can consider it as an inner product, A times A, right? A square and B square, C square, D square. We can times them together. So this is A square plus B square, C square. So this is summation of them. Right? So if we go into each item, summation matrix is just take summation of each one. Okay. So this is how we can observe this. So first outer product and then the summation. Okay, because we need to unfold along the row direction. Right? So of course the first row is a column. Right? So but we take the transpose. Okay. Yeah, I hope this is you can visualize a little bit. Okay, so another thing is that y equal to dt times r. This is not difficult to see. Right? So first row times this is again a summation. Okay, a summation. The second row, because you have one more xt, the third row you have another more xt. Right? So each time, this t is changing with each row. Okay, and that's why we have. Okay. Any questions? Oh, by the way, this is transpose. So this after transpose, 111 is the first row. Okay, 111 times this inner product, it's summation. Then it's this is the second row times this. Okay, this is the third row times this. So that's why we have this power. Okay. Yeah, again, you can put it offline and think about it. And in our first written assignment, we will ask you to do this again, using what we derived, the multivariate calculus. If you go from there, it will be super simple. You don't even need to do things like this, right? So you need some experience to see through them, right? If you use the multivariate calculus, the linear form, the projective form, you will immediately see this. You don't even need these element-wise consideration. Okay, that's the power of the multivariate calculus. Okay, and keep in mind you will see that. And now, if we know that, so we have A times W equal to Y, right? Where A is dt, Y is this, right? So basically we are saying that A is dt times W, right? So equal to Y. Y is dt. Okay, right? So if we just time the inverse of this on both sides, the dt b inverse, and this you also time this, right? And then you get this. This inverse cancels, which gives, right? So this is how we derive this. And this term here, this term has a name. For these squares, we know that this is called the pseudo inverse of D, right? This is called the pseudo inverse of D. Okay. This is like inverse, but when you take inverse, you have to have a square matrix, right? Only a square matrix can take inverse. Pseudo inverse is like inverse, but you don't have a square matrix. Right? So, for example, this matrix basically tells you, along this direction n, right? How many data you have. But along this direction is k. Right? So a k plus 1. Right? So this is more like to the x to the power 0. Okay, so the dimension doesn't match for non-square matrix, if you take inverse, it's called pseudo inverse. Right? So this is actually, let me see. Yeah, so let me, maybe it's better if I show you the website. Yeah, so we can move this website here. Okay, so this is a pseudo inverse, which in Wikipedia explains the form. Okay, so it's basically this. Okay. There's other definition, but it's basically this. Okay. This star, they use star instead of transpose, right? So the reason I think the star is called Hermitian. Okay. Hermitian is something similar to transpose. Okay. The difference is this. So you are considering complex domain. So instead of just taking transpose, you also take the complex conjugate value. Okay. So which means if you previous A plus BI, now you should minus BI. Okay. Instead of just the inverse for that. I think that there could be example. But anyway, so we are not considering the complex domain, so it's not so important. Okay. Let's come back. Okay, so now previously we have seen the squared error, right? So squared errors. Okay. But we can define many other errors. Right. So square error has a relationship with the maximum likelihood estimation, right? But the other errors may not have that relationship, but they also are meaningful. Okay. So square error basically says if you have a value that is very far away from the reality, that will penalize your value a lot. Right? If you have a distance 10, square is 100. If you have 100, distance to the real value, square is 10,000. Right? So that matters a lot. You do want to pull everyone relatively close, right? You don't want someone to lag behind. Okay. And there's also a concept called relative square. So what does this mean? So, so let me see what it can. Okay. So maybe you have some values like this. Okay. And of course, the error is going to be big, right? So because they are scattered, right? So there's another error, something like this. Okay. They are not so much different, right? So, but if you think about the relative difference, right? So actually they're similar, right? So maybe for this value, your prediction is far away by this, right? This is far away by this. This is far away by this. This is this. You have a little bit smaller difference, right? But you know that proportionally, they are kind of having the same error, right? It's just the absolute value difference, right? So you want to normalize it. But how to do that? You take your y values, your r values, right? You compute their sample values, okay? You compute their sample values, right? So, and then you normalize it, right? So you say, hey, for this, maybe their variance is 10 and your distance is 1, right? It's like if your variance is 1, the distance is maybe 0.1, we still consider they are relatively equal, as the error rate is equal, okay? Because your value, absolute value ranges are just 10 times larger, right? So this is called the relative square. Okay, we do normalize using the variance of the R you observe. Okay. So there's also a concept called absolute error. Okay, absolute error. And absolute error, instead of taking square, you take the absolute value. Right. So what's the difference here? Right. So the difference. Let me give a example. Okay. So just think about it. Right? So let's say you have a line here, and you are a little bit different from here. 1, 1, 1, 1. Okay, and then so this is one different from the true value. Another case is, hey, these values are all on the line. But this guy has a big error for, right? For relative error, it's the same. Okay, you are just summing up 4 ones, or you are just having 0, 0, 0, and 4 summation. Okay, right. So, but for square error, that matters a lot, right? So you know, it's if you think about 1 square, 1 square, 1 square, 1 square, sum them together, it's 4. Okay, but if you have 4 square, it's already 16. Right? So you don't want someone to be too far away from your prediction. Okay, even though the other side. You want to pull this relatively closer, even though the others may make some mistakes. Okay, so that's the difference here. But they are just from different perspectives. Usually, in an experiment, you will report all kinds of errors and show, hey, your model is better than the other model in all these errors. Okay. So there's also a similar concept like absolute error. Okay. So for example, usually we will also consider, let's say there are n items, we will divide by n, right? So because then we will see how likely each error squared is looking at, right? So here we are taking a sum, the n errors summed together, right? Another important reason we always consider mean square error is because, you know, we don't want the number to explode, okay? Because when you take summation and each error is big, like 1,000, if you take so many data, the number can explode. And our number in computer has limited precision. So this is, I think, the key reason why people stick to mean than just a sum in, you know, like say in deep learning programming. Okay. So this, if we also divide by n instead of by 2, right? This is called the mean square. N mean, yes. Okay. So if you further take square root, this is r. Okay. And this relative square error is called the RSE. Right. So then you want to take the mean, the m RSE. Right? So this absolute error A, and usually we will consider mean absolute error, MAE. Okay, there's also a similar concept from square side to the, you know, to this one. This is called the mean. I don't remember. Let me Google a little bit. Yeah, let's see. Okay. Yeah, it's this mean AP, MAP. Okay, MAP. Right, so. So something like this. Your actual value, your predicted value. Right? So you normalize by the actual value. Okay. So this is called the percentage deviation. Okay. This is an MAP. Okay. So these are just if you see that in the paper, hopefully you know what they're talking about. Okay. So usually we will evaluate a lot of them. Okay. So let me see. So. The last error is called epsilon insensitive error. Okay, so why we need this error, or what it is talking about? Okay, this is an indicative error, meaning if your condition here is met, it will be 1. Otherwise, it will be 0. Okay, so this is basically saying that if your error to the true value is less than epsilon, this term will be 0. So the summation is adding 0. So you will not contribute any error to the loss function, to the error function. Okay, right? Only when you are different from the true value by more than epsilon, right? This start to be 1, and you start to penalize, right? Even though you start to penalize, right? So let's say this is epsilon, right? You already have more than epsilon. Let's say you have k far away from it. Okay, the error is not k plus epsilon, right? Even though you are distance k plus epsilon to r, you only count the k. The epsilon is still not counted. So you minus epsilon when you count the error, right? And this is turning out the constant. Okay. We can actually pictorially visualize it. Okay, let's go to the browser. Let's see an image. Yes, that's basically right. So if your distance to the true y hat is your guess value, right? So y is the true value. If your distance to the true value is less than epsilon, you have no loss. You have no error value. Okay. If you start to go beyond that, let me use a pen. It's now instead of epsilon, right? So you go beyond epsilon to the true value by 1, okay? Then your y loss function on this direction, right? So here it's still 1, okay? It's not 1 plus epsilon, right? The epsilon is always given, right? So this is basically saying if you are within epsilon, we don't count your error, okay? Starting going beyond epsilon, we start to count error, okay? So this is actually useful for some models to avoid the sensitivity issues, okay? Like there's a small difference of the noise. If you don't have this error, it will cause a lot of trouble. But this is model specific. We will see that in support of machine and probably 2 lectures later. Okay, but keep in mind there's a loss function like this. Okay, clear. Very good. Yeah. So let me see what's the time now. Okay. Yeah. For example, if you look at let's look at a particular paper. For example, traffic prediction graph. So some, any paper that can, let me see. I think there's a paper called the T spatial temporal something like this. So, for example, this is a paper using machine learning model to predict the traffic. Right? So, and if you look at their experiments, they have all these things. Right? So RMS mean square error, and then you have the mean MAE and the percentage one, okay, and the root mean square. Right? So they compare different error metrics and show that hey, our method always is better, right? So if you're MAE, the other model is 3.5 and I'm 2.2, right? So for MSE, the other model is maybe 7 something, 6 something. Right? So this is a way that if you are doing evaluation, you can test all the errors and show that you are always better than the others. But this is the strongest signal, right? Maybe in some metric you are better, others are not so better, then it's weaker signal that you are better, okay? So that's why we're talking about. Okay, so next, let's take a look at the, oh, by the way, any questions so far? By the way, this is just for regression. Okay, for classification, you use accuracy. This kind of thing, okay, accuracy, F1 measure, record, this kind of thing, for binary. Okay, let's consider. Okay, now if you think about, we have a randomness, right? So because of the randomness, so we will not prove this here, okay? But we actually already proved this before. Let me show you. We have looked through the proof that we will add a term and a minus term and then add a term, and then we can have the variant term and this kind of things, right? So using exactly the same derivation that I will leave to you guys for practice, okay? We can show something similar, right? So because we have the sigma square white noise to the Gaussian distribution, right? So we need to take a fluctuation, right? So the actual value is no longer a fixed value, right? So we have some Gaussian component in it. Okay. Then if we take the expectation, right? So it's square of the error, right? So error is like the bias distribution, right? And then the error square expectation. This is like the variance, but it's not. Okay. But this is just for a particular data item X and R, right? So we are taking fluctuation over the white noise, the variance of the white noise. Okay. So we have some conclusion similar. That's a pi square plus the length. But here it's noise, okay, and it's error. Okay. So one conclusion we can see is that only the first term depends on the estimator G. Okay, only the first term is on G. The second term is not on G. What does this mean? The second term is really on your data. Okay, so X and the Y are the data, if you remember. That's the data. So this is really the data noise. Okay, so the sigma squared. How likely your measurement of R adds noise to your predict fx. This is totally on data. Okay, our model's error. Well, even if you use a model 100% accurate, 0 error, we will still have this noise. Okay, So this is what it, let me clear this. Now, so far we take the expectation over what? Over the white noise for a particular data item XR, okay? Now let's consider the model over a sample data, right? So a bunch of data. So for example, if we consider, maybe that's a bad choice. Yeah, instead of one data item, X and Y, X and R, right? We have a bunch of them, all the cross points, okay? We have a lot of them, right? If that happens, let me see where we are. Then we want to take a different kind of training data, right? So maybe you split 80, 20, right? So the different 80%, right, are sampled randomly. Then there's another randomness come from the data samples, okay? And this is like what we derived last time, right? So if that is the case, you can also show that if you take a expectation over the data set, okay, you will show that it's the same. It's the derivation is exactly the same, okay? It's a bi-square plus variance. But this time the randomness is introduced by the data set. Okay. Any questions? Okay, so let's continue then. So here, why we need to show this? Because previously we talked about classification using discriminant function. Then introducing white noise, and we discussed the regression. Right? So regression is still bi-square plus variance. Okay. So then for any machine learning model, it's always bi-square plus variance. Okay. The error is always equal to bi-square plus variance. Okay, the loss of the error. So let's see the trade-off here. You know, we have the model complexity. Let's consider polynomial. It's order 1, order 0, order 1, order n. Right? So whether it's linear, quadratic, order 9, right? So as you increase the model, right? So your bias will decrease, right? Because your training data, you can fit it better, okay? As we see in the first lecture. But your variance will increase. Right? So I think I don't have the first lecture anymore. Right? So let's go back to the, unless we open another. This is 42. So let's go back to this example again. Right. If you use a high order curve fitting, right? So you will do something like this. Right? So right. Then this will have a lot of variance. Right? So next time, if you have another x, you want to predict this x value, it should be something around this line, right? But you will predict the value to be here. Right? So there's a large gap. This introduces a lot of variance if your model is complex. Okay. Let's go back to that page. Okay, so as your model becomes more and more complex, your bias will decrease. You can fit your data better, but the variance will increase. And the variance itself can kill performance because you will test it on unseen data, right? On unseen data, your variance is big, right? So you know, even if it's unbiased, right, it's 10, but your variance is 8, right? Then it becomes 18 or 2, right? So it's not accurate at all. Okay, so there's a optimal model that's not too complicated. Bias and variance are having trade-off, right? So bias is decreasing, variance increasing, right? There will be some trade-off that you have the smallest error. Okay, to do that, you have to do that on a validation set that is not on your training data. Right? So all you can do is you increase the model complexity, the hyperparameter here, and then you see which one generalize, which one perform the best on the data you never see in the training. Okay, so this is called the model selection process. Okay, so the grid search CV means cross validation. Okay, so cross validation measures the generalization or accuracy by testing on data n used during the model training. So you will have to hold out 20% for validations, right, and the other 80% for training. Okay. So regularization, usually you will have a regularization term, which is cancel the model complexity. Right. So lambda is a regularization term, right, and this is the data error. Okay, but you also have a complexity parameter. Right? So when you do this, right, you will not tend to make your model too complex. If you have a parameter that makes your model too complex, this term will be big. So your resulting error will be big. And we are minimizing it. Right? So we will sacrifice a little bit the error, but we will try to keep the model simple. Okay. And so next is Bayes model selection. Okay. Bayes model selection is used when there exists prior knowledge about there's a prior knowledge, right? Bayesian estimator. Right? So whenever we take Bayesian, it means we want to use the Bayes formula. You have posterior, you have prior, you have the observed data. Right? So then you have the generic model. Okay, these three terms. You keep all these three terms in mind. You know what is generic model. Okay. And now we need to consider prior also into the model. We have the Bayes model selection. Okay. And then we want to pick the posterior. Right? So the posterior, the best model when you see the data, actually not only depending on how the model generates the data, but also how likely you believe it's, let's say you believe it's a quadratic or it's linear, not it's orthogonal. Right? So this, if you introduce this and the prior is really correct, that will improve your model selection. Okay. And once you get the posterior, you can select the highest posterior, the model with the highest posterior. Right? So you can also choose multiple models with high posterior. Then you can use the ensemble method. Right? Let's say if it's regression, you use these three models that are all very accurate. Right? And then you compute the regression value and then take the average. Right? So then it's an ensemble method. Okay? I will leave ensemble method to data mining course. Right? So this is a topic that definitely will be covered in data mining. So we will ignore that in machine learning course, unless you know it already. You know what I'm talking about. Okay. And we can also use all models. If we use all models, we need to weight by the posterior probability. Right. So this is exactly, let me see. Bayes, I think this is exactly what we talked about in the beginning of today's lecture. Right. So let me try to find it. Okay, it's too many pages early. This is exactly here. Okay, so Bayes estimate. Okay. So we take the probability of model one, like linear model, quadratic model, etc. Right. So the probability along with the model prediction values. Right. So we are taking, we consider all possible models, but some models are less likely. Right. Some are more likely. Okay. We basically take an integral. Weighted sum is because the models are discrete. Right. So we take a summation. Okay. So this is 22. Let's go back to 43. I think. Yeah. 43. So you can use this method to select the best model or a sum model. Okay? And the regularization is actually, you can see it as what? As the prior. Okay. Right. So for some models, you don't know how to do regularization, right? So here is what we need. Okay? If you know the prior, you can add the prior. Okay. If you don't know the prior, you can still do the regularization. Okay. So you think about it, because this data is constant, right? So we don't care about it. If you take the log of this, it's equal to what? It's equal to log of this time plus log of this probability, right? And this is a log model. This log model is basically equal to your, plus this is also, right? So in our loss function, we usually define something like a plus the L2 normal BR, right? So this thing serves as a prior to the model, right? Saying that, hey, this model is not likely to be too complicated. Okay, right? If it's too complicated, probably will drop. That's it. Of course, when we talk about loss, this loss will improve. Right? They're reversed. Okay. Any questions? Yeah, if not, we will continue because we are running out of time. I don't think we can. Let's try to go through a few more slides, and then upon where we need to do some derivation, we have to stop because 22, 8 more minutes. Okay. So next we look at multivariate data. Okay. So previously we are talking about this kind of data, right? So we have a label, like whether it's regression or classification. This classification, this regression is R. Right? So there's also that's the estimation of P. So this is one value, and here we only have x1, right? So because it's a univariate. Now we consider multivariate, which means we have a bunch of x1, x2, x3. Well, keep in mind, even for univariate data, right? So there may be more than one parameter, like Gaussian, mu, and c, right? So it doesn't mean that we don't need high dimensional, the multivariate capital. Right? But multivariate data is more complicated, right? So even the x itself is high dimensional, right? So this means the function itself, the distribution itself is high dimensional. So the distribution function itself is more complicated, okay? Like a high dimensional Gaussian distribution. So that's why we first talk about simple case, and then we talk about a little bit more complicated. Okay, so what is the multivariate data? Okay, so the multivariate data, basically there are multiple measurements, right? So made on each event. Right? So generative observation vector. So how to say this? So basically, this is what we mean. Right? So we usually model them as a matrix. Okay, it's actually just a table. Okay, so this is the first attribute. Right? So this attribute ID. This is the second attribute. And so this is attribute 1, attribute 2, attribute D. Right? So we have D given D variable because each attribute we treat it as a variable. Okay, and we call it attribute or we call it features. In machine learning, we usually call it features. Right? So if you are in relational database, we call it attribute. Right? So yeah, so you can use F also. Right? So, and these rows are what? These rows are data. The first row, the second row, and the nth row. So we have n. Okay. So that's just a rephrase of this thing. But we do have those notations clear. Right? So we have d-dimensional d attributes, d features. Okay, we'll have n data. Okay, so this is what we want to see. And another is IID instance, which means hey, this line is sampled from a distribution, d-dimensional distribution data, right? And this line is sampled also from this distribution, right? Identical distribution and independent, right? And when we sample from them, there's no correlation. Right? I sample this from here. I sample also this from here. They are not dependent. Okay, so this is basically our assumption on the data. Yeah, 5 more minutes to go. And so for classification regression problems, we are predicting, those variables can be, each variable value can be either discrete or continuous. Right? So continue, in here we usually consider continuous values, okay? And that could be also discrete values, like male, female, right? So, or maybe GPA, right? Or maybe the rating, right? So 1 to 5, okay? So they can be discrete. And then actually, between discrete and continuous, there's also another concept, right? So one is called categorical. Categorical is always discrete. So like male, female, like bird, dog, cat, okay? But there's no order. There's another term called ordinate. Right? So the order matters, right? So whether it's between 1 to 3, this is continuous, right? 1, 1.1, 1.11, 2.99, right? So it's continuous. But there could also be discrete, right? 1, 2, 3. But there's order between them, okay? And while this cat, dog, and etc. categorical, there's no order, right? So these are the different concepts. I think in data mining you will go through these, okay? And for different type of attributes, you need a pre-processing to make the machine learning model fit, because machine learning usually work on continuous ordinal values, right? So there's pandas. Pandas will provide all kinds of pre-processing. Pandas are reading your table, some table like this, okay, in Python. Then you do pre-processing, discretization, etc. So try to make a, make an attribute like one-hot encoding. Right? So for categorical attributes, like cat, dog, and maybe bird, okay, you will make it 3 attributes, okay. Cat is maybe 1, 0, 0. But dog is 0, 1, 0, 1, okay. Maybe bird is 0, 0, 1. This actually makes sense, right? So this is whether it's cat or not, whether it's dog or not, whether it's bird or not, right? So they are independent attributes. Right? They are meaningful. Okay? Instead of just encoding them in 1, 2, 3, whereas order. Machine learning model will always consider ordinal attributes. Okay. Any questions? Okay, now then let's continue. Right. So, yeah, there are some concept. Let me see time. Okay, so I think it's almost there. Yeah, I will stop here and continue next time. Hopefully next time we will finish this slide. Okay. Yeah. Any questions? If not, that's the end of the class. And yeah, so I will be here for 2 more minutes in case you have questions. Okay.
Professor, I have a question regarding the grid search.
Okay.
So though I'm using the F1, I'm actually using the F1 weighted average because F1 basically deals with the binary, and since it is a multi-class problem, I'm going for the either weightage or micro or macro. Can you tell me the difference between?
You speak too fast.
Okay.
Yeah.
So the thing is, I am using F1 score,
Okay.
but I don't know whether I have to use micro or macro or weighted average, weighted F1, because F1 only deals with the binary classes, but here with the digits data, we have more than 2. So which one do you think is?
Actually, yeah. So there's a actually I don't know. I know that for particular like biomedical data, they just look at the micro. So you can look at the difference. See whether there's some recommendation.
Yeah, I checked with the micro, macro, and weighted, but I'm not really sure which one to use when. Like, since this is a digits data, I'm like, this is just predicting the digit based on the attributes. I'm not really sure which one to use because this
Yeah,
is not so sensitive.
Yeah, you can look at like Google and about micro, the results. I think if you look at I don't think they have a tick one. So let me see. In a multi-class clustering settlement, micro average is preferable. Right? So if you suspect there might be class imbalance, okay? Right. Yeah, so basically if you know that your class imbalance, that's why in medical data, usually people use micro. Because you think about it, if you have healthy people, right, control, and then you have like disease people. Usually disease people, maybe most people are not sick, right? So it's just a routine examination, right? So in that case, it's an imbalance, okay? If it's imbalanced class, right? So maybe 2 people have cancer and 98 people are healthy, then probably you should use a micro, okay? But if you are pretty sure it's
classes, right?
balanced, you use micro. Right, so according to this answer, but this answer also not ticked, so I'm not really sure. Okay.
Yeah, I got the understanding. So I'm using weighted because the classes are balanced, right? Or I mean, we have 10 classes, so that is why I'm not able to decide whether I have to use micro.
Oh, so weighted F1, right? So let me see.
Yeah, then I'm looking for weighted
so how
F1 measure.
How do you set the weights?
It's basically taking the F1 measure for each class and doing a weight on that particular data point.
So let me see. So you use scikit-learn, right? So
yeah, I read from the same thing.
Yeah, let's see. I think maybe they have a way to set the weight. Okay, so let me see. Yeah, here's the explanation. Oh, so they are, you know, actually, this alters macro to count for, macro is not considered label imbalance. So weighted actually considers the label imbalance, right? So basically this alters macro, okay? Right.
Yeah.
Yeah, so I think then they have the sample, no, this is sample weight, right? So this should, they should have how they compute the weight, right? So I think this is based on I believe it's based on the class. like let's say how many classes you have. If you have let's say only 2 people, right, in with cancer, then their weights are higher. Okay, if you have 98, that would be lower. I think they have a formula to do that. Okay? I think that one you can do that. Definitely, you can do that. Okay.
Yeah. So,
Yeah,
and I'm also not sure about the C value. I mean, I did not quite get the C value in, C parameter from the model, from the SVC.
SVC, right? So SVC C value is the regularization. Okay.
Yeah, I did not quite get that.
The lambda. Okay, it's the lambda here.
Right.
Yeah. So you know, depending on how much you want to reduce the model complexity, if you want to reduce complexity, you add a C value. But it doesn't really matter. You just use the grid search CV. I see which C is the best. It's okay.
No, I'm basically doing the two things. I'll share the screen. I mean,
and I can tell you. So second-learn's default parameter are not too far away from optimal in most cases. So they have all kinds of tests and they find almost the best one, right? You fine tune a little bit, you'll find the best one. It's never going to the bad cases. Okay, second learn, if you don't tune the parameter, it's already very good. If you further tune it, it will be better. Okay.
Okay. So I'm taking from 1 to 5. So the only question which I wanted to ask is the C value, by default, the C value is 1.0. Yeah. And I mean, it was not mentioned whether the C value's range is from 0 to 1 or 1 and higher.
0 to 1.
Regularization.
Oh, C value, you can try higher than 1. Okay.
Yeah.
Because
okay.
The definition is a little bit different from L2 regularization, L1 regularization. Okay. So there's some difference. But it's a regularization term. C is a regularization term. Okay. Right. If
so
C
it
is
can be
larger
1 or higher.
Yeah.
So I'm trying with 1, 2, 3, 4, and 5.
Oh no, I think you should foresee you should try in the order of 10, maybe 0 0.1, 1, 10, etc. Okay, aggressively.
I did not understand that, Professor. Can you please repeat it again?
Yeah. So what I mean is you should not just try 1, 2, 3, 4, 5. You should first try aggressively. Maybe see is 1, 10, 100, 0 0.1, etc. And then find a good range. Then you can.
Okay.
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 Yeah, and yeah. So I'm not really sure. They seem to say that you can provide a sample weight, right? So you can also provide a weight. So F1 score, you can also provide a weight. So basically, according to what I understand, the weight is provided by you, right? Like cancer, I give 10. And
I mean, the weights we can, I mean, how can I say this? Okay, it's just like we can add custom weightage to each class.
Yeah,
so
exactly.
Here.
Yeah, so do you do you use theirs? I mean, if you don't have this, maybe they will compute the using some formula.
Yeah, I mean,
according to the how many labels you have. That's the cancer.
No.
Otherwise, you need to provide the weight. I'm not sure. I haven't used this before. So
no, I mean F1. This is completely different, Professor. NP.average. No, I don't think this is the one. So while defining the F1 score itself, we can mention the average technique. It can be selected either from this is giving the weights manually for each class, but this is not for that one.
Okay. So you mean that it should be this function, right? Not the average. Okay, yeah. So I think because I haven't used the weighted F1.
Yeah.
So we need to study a little bit. I think there must be some instructions.
I just tried, but the only thing which I'm missing is while using the grid search, I'm not able to print the results where it shows F1. It's just showing the mean test score. Like it's performing 4 sample tests out of the given data, and it's just giving the output. So that is where I'm confused.
I don't quite understand the question.
So while using the grid search, it will compare with all the parameters and give you the best model parameters, right?
Yes.
So, but I cannot simply trust on that because here it was asked to find all the F1 parameters, I mean F1 values for all possible combinations. Do we need to print that?
You mean assignment?
Yes.
Assignment, you just need the default F1 measure. I think it's a macro. Okay, you don't need to have all kinds of F1 measure.
Okay.
Yeah, the default one. Okay, so I think the default one is macro. Okay, F1. Yeah, we didn't get into the details of those values, so it should be the default one. Let's see. Oh, default is binary. Okay, so
Default is binary. That won't work because here we have more than 2 classes. Hence, we cannot use binary.
Oh, I see. So then you can use macro by default, or you just use a macro. Okay, macro already considers, you know, label imbalance. Okay, you can use macro. You can use macro. Okay. Oh, let me see. Yeah, actually, we don't restrict you on which one to use. As long as it makes sense, it's fine. Okay.
Okay, Professor. So do we have to print F1 measures? I mean, F1 score for each combination, or do we just have to find the
find
one
the
which
best
is giving
one
the maximum?
You find the best one.
Okay.
Okay. Yeah.
Okay. If I use the grid search, I'll not be able to print it for all the possibilities.
You can still do that. I think grid search, right? So for any machine learning model in scikit-learn, you have excuse me, verbose. Okay. This verbose, if you set it to a high value, it will print everything. Okay.
Okay.
Yeah, it's a higher the more message. Okay. If you print it to high enough, maybe 2, it will print each time what's the parameter, what's the F1 measure.
Okay.
Yeah.
I'll try that.
By default, it may be 0 because when you use the model, you don't want to print too much. Okay. If you set to 2, maybe the problem solved. Okay. Yeah. Any other questions?
No, Professor.
Okay then. Yeah. So I will have to leave because I have a paper deadline very soon. But feel free to message me in Canvas or email me. Okay. I will answer your question. Thank you.
Sure. Yeah.
Bye.